Okay, so we're going to have a look at another question from the electromagnetism topic. We're told a bubble enters an electric field generated by two parallel plates with an initial velocity of 0.5 meters per second downwards. The bubble's mass is 0.001 grams with a charge of 1.5 nanocoulombs. The field, we're told, has a strength of 500 volts per meter. What distance does the bubble travel after 1 second? And find its velocity when time is equal to 1. We're told for this question to neglect gravity. So we're going to ignore the acceleration due to gravity. We're just going to think about the accelerations due to the field. So the bubble will sort of enter here. We have a little picture of a field. And it has an initial velocity downwards. It has no initial acceleration, but it will gain an acceleration once it enters the field. So we have quite a bit of information here. Let's set up our accelerations and then our velocities, then our positions. So acceleration in y, if we choose this to be positive y, this to be positive x, our standard Cartesian system, acceleration in y will actually be 0 in this case. And acceleration in y will be 0 because there is no gravity and the bubble is not accelerated downwards by the electric field. The bubble will be accelerated horizontally by the electric field. So acceleration in y is 0. Acceleration in x, on the other hand, if we think about this bubble, it has a positive charge. So we're told 1.5 nanocoulombs, that's positive. That means it's going to go to the right. So it will have an acceleration to the right. The magnitude of its acceleration will be its charge times the field strength divided by its mass. So its charge is 1.5 nanocoulombs. So 1.5 nanocoulombs is 1.5 times 10 to the minus 9 coulombs. So this is just a conversion. So 1.5 times 10 to the minus 9. We are told its mass is 0.001 grams. So that's 1 times 10 to the minus 3 grams. If we divide that by 1,000, that is 1 times 10 to the minus 6 kilograms. 1.0 times 10 to the minus 6 kilograms. And then the field, we're told, is 500. So E is 500. So we plug all this in. 500 divided by the mass, which is just 10 to the minus 6. You can have 1 times, but you don't need to. Now we're going to plug this into the calculator. 1.5 times 10 to the power of minus 9 multiplied by 500 divided by 10 to the power of minus 6 gives me 3/4. So the acceleration in x is going to be 0.75 meters per second squared. So now we have the accelerations in y and the acceleration in y and the acceleration in x. We can calculate the velocities. So these are accelerations, velocities. The velocity in y will be the initial velocity. So we were told there's an initial velocity of 0.5 meters per second, and that goes down. So the velocity in y will be minus 0.5 meters per second. The velocity in x will be 0.75 times time plus the initial velocity in x. There is no initial velocity in x because it doesn't start with any sideways movement. So these are the two velocities. And then the positions, we'll find the position in y is going to be minus 0.5 times time. And then the position in x is going to be 0.75 times time squared divided by 2. And that's it. You'll notice there is no y0 or x0 in this case because we choose the particle entering the field to start at the origin. Right? You get to choose where the origin is in these formulas. We're choosing the point where the particle enters the field to be the origin, just because it's convenient. You don't have to, but we're going to. So now we have these accelerations, these velocities, these positions. What distance does the bubble travel after 1 second? Okay, so we need to evaluate the positions when time is equal to 1. So find position in y and position in x when time equals 1. So position in y is minus 0.5 times 1, which is just minus 0.5. Position in x is 0.75 over 2 times 1 squared, and this is 0.75 over 2, so it's half of 75, so that's 0.375. 0.375. So it's gone down by half a unit, it's gone down by 0.375 of a unit. Therefore, its net change in position will be the square root of the sum of these squares, square root of the sum squared of the individual positions. So position net is the square root of position y squared plus position x squared. This is the square root of minus 0.5 all squared plus 0.375 all squared. So the position, the net position, or the net displacement from its starting position as a vector, square root of negative 0.5 squared plus 0.375 squared gives me 6.25 times 10 to the minus 1. 6.25 times 10 to the minus 1, and this will be meters. So this is the answer to part A. For part B, we've been asked to find the velocity when t is equal to 1. So to find the distance in x and y, we evaluated these when t was equal to 1. To find the velocity when time equals 1, we evaluate the velocities when t is equal to 1. So our velocities are v of y is always 0.5. v of x is 0.75 times t. So we're going to let t equal 1. This tells us that the velocity in y when time is 1 is minus 0.5. It's a fixed velocity in y. Velocity in x when time is 1 is 0.75. So if we draw a velocity vector diagram, we're going down by 0.5 after 1 second, and we are going across by 0.75 after 1 second. So the velocity vector looks something like this. This is Vy, this is Vx, this is V. So again, V will be equal to the square root of the sum of squares, Vy squared plus Vx squared. This is the square root of minus 0.5 squared plus 0.75 squared. So therefore the velocity after 1 second is the square root 0.5 squared plus 0.75 squared, and that is 9.0138 ... times 10 to the minus 1. And we might round this, let's say 3 significant figures. Let's say velocity is 9.01 times 10 to the minus 1, and this is in meters per second. So the change in position was in meters, the velocity will be in meters per second, and this is the answer to this question.